So now we're going to look at a few more examples of trigonometric limits. The first example is the limit as x approaches 0 of sine of 3x divided by 3x. This looks really similar to what we saw before. We looked at previously the limit as x goes to 0 of sine of x over x. But here we have a 3x. And I want to introduce the new technique, which is called a change of variable technique. And it works exactly how you want it to work, variable. We're going to set a new variable and call that variable theta and set it equal to 3x. So set theta equal to 3x, and the name of the variable is up to you. You could call it t, you could call it s, whatever you would like. And we notice that as x goes to 0, 3x also goes to 0, right? Because just 0 times 3 is 0. So that means that as x goes to 0, we also have that 3x goes to 0, and that will mean that theta is going to 0, because theta is exactly equal to 3x. And we need to make sure that when we change the variable, that the limit on this new variable will be the same as the limit on the original variable. And that means that we can rewrite this expression instead, that this limit is going to be exactly equal to the limit as theta goes to 0 of the sine of theta over theta. And as we discussed previously, this limit is exactly equal to 1. And that means that we're done. So by our change of variable technique, we rewrote this limit to be a limit with a new variable that we knew how to construct the limit of. So this is a limit of 1. That's one example. Let's see that in a more complicated example. So let's take a look at the limit as x approaches 0 of the tangent of 4x divided by 9x. This looks crazy and complicated, and I'm going to break it up into a couple of pieces. How can we approach this? We don't know how to deal with tangents, but I'm just going to use some some trig identities to be able to write tangent is the same thing as sine of 4x, let me move that down, divided by the cosine of 4x, right? That's just rewriting tangent, and all of that is divided by 9x. So by properties of fractions, I can rewrite this a second time, and this is going to be the limit as x approaches 0 of, let's write it as 1 over cosine of 4x times sine of 4x divided by 9x. This gets us a little closer to things that we're familiar with. This is something that's close to what we've talked about in the past. 1 over cosine of 4x we're going to have to deal with separately, and we can actually think of this as a product. We know that in order to apply product rule, we're going to have to, both of these pieces are going to have to be defined, and we're going to have to do a little work to make this look like what we want it to look like. But notice that this first product, as x approaches 0, the cosine of 4 times 0 is the cosine of 0, but the cosine of 0 is equal to 1. That's the x-coordinate when your angle theta is equal to 0. So this whole first part of the limit is actually equal to 1. So let's break this apart. We see that this is the limit as x approaches 0 of 1 over cosine of 4x, which we know that this limit is 1. And then this piece, we don't want to have 9x in the denominator, right? Because the 9x doesn't match the 4x. We can't do a change of variable technique. So I'm going to change this 9x into a 4x by multiplying it by 4/9. And if I multiply the denominator by 4/9, I also have to multiply the numerator by 4/9. This is another clever bit of trickery. Sine of 4x, 9x. What does that clever multiplication give us? It means that the 9's cancel and the 4 happens, which means that this is exactly equal to the limit as x approaches 0 of 1 over the cosine of 4x. The numerator becomes 4/9 times sine of 4x divided by, the 9's cancel, I'm left with a 4x. Phew! Right? So this is just a distributive property. I can, or here in the denominator, this 9 cancels with this 9, and that's where I get the 4x, and in the numerator, I'm just leaving that as 4x, or 4/9. So, what can I do now to evaluate this limit? The 4/9 is a constant. By our limit laws, I can put that in front of the limit, and I'm left with 4/9 times the limit as x approaches 0 of the cosine of, or 1 over cosine 4x times this known limit, and we know what this limit is. Maybe I'll write it out. Times the limit as x approaches 0 of sine of 4x over 4x. By our change of variable, letting 4x equal theta, we know that this limit is equal to 1. This limit is equal to 1 as well, and we're left with just the 4/9. That's one of the more complicated examples that you could see applying our change of variable technique that we just saw. And finally, we're going to do one more example. In this final example, let's take a look at the limit as t approaches 2 of t squared minus 4 times the cosine of 1 divided by t minus 2. And I'm going to use the fact that cosine, here's my unit circle, we did it with sine in the video, but cosine is always bounded between 1 and -1. Right? Because our x-coordinates on the unit circle can't get any bigger than 1 and can't get any smaller than -1, meaning that the outputs of this function are between 1 and -1. Let's see what that means for this entire limit. If my cosine of 1 over t minus 2 is always bounded between 1 and -1, I'm going to multiply by t squared minus 4. Careful though, we need to be careful because t squared is always going to be positive, but t squared minus 4 is not always positive. In fact, t squared minus 4 is going to take on a negative value for values where t is between -2 and 2. So we're going to have to look at this in terms of a piecewise squeeze theorem. So as long as my t values are between -2 or outside of -2 and 2, we're going to be left with the negative of t squared minus 4 is less than or equal to t squared minus 4 times the cosine of 1 over t minus 2 is less than or equal to t squared minus 4 if t is less than -2 or if t is greater than 2. And what does this simplify into? This is 4 minus t squared is less than or equal to our expression, t squared minus 4 times the cosine of 1 over t minus 2 is less than or equal to t squared minus 4. And then let's go ahead and take this limit. This is a continuous function. When I take the limit of each of these chunks, the limit of this, because this is a continuous function, I can actually just plug in 2, and I get that this limit is 0, is less than or equal to the limit as t approaches 2 of what we were looking at, squared minus 4, cosine of 1 over t minus 2 is less than or equal to, whoops, maybe this notation is bad. I should have 4 minus t squared here, just for the notation, just to keep it consistent. T approaches 2 of t squared minus 4, and again, this is a continuous function, so I can plug in 2, and I see that by squeeze theorem, my limit is bounded below by 0, and my limit is also bounded above by 0. Because as I plug in 2 into this function, the continuous function, I also get 0. That tells me that my limit is in fact equal to 0. Now, for precision's sake, I would have to do this a second time, flip-flopping the inequalities. But we see the inequalities, it doesn't matter which bound is on which side, it's going to be 0 either time. And so we see that no matter what, by squeeze theorem, our limit is in fact equal to 0. By squeeze theorem, we get that the limit as t approaches 2 of t squared minus 4 times the cosine of 1 over t minus 2 is in fact equal to 0.